Hello, welcome. And my name is David Shaw. Welcome to Simplifying 5-Axis Programming with GibbsCAM. For the next 30 minutes or so, I'll be showing you how simple creating 5-axis toolpaths can be with GibbsCAM. As the presentation progresses, if you have any questions, enter them in the Q&A panel on your screen and we will answer as many as we can at the end of the webinar. Over the last 38 years or so, GibbsCAM has built their reputation by simplifying complex CNC programming. Part of the simplification is simply organizing the information and parameters needed to fit the way a machinist thinks, the way that a machinist basically approaches machining a part. By effectively streamlining and organizing the input of parameters and minimizing how many parameters you have to deal with, GibbsCAM shortens the learning curve, greatly reduces programming time, and most importantly, leaves you in control of few or as many of the details as you want or need to be in control of. All right, so here's the part we're going to be looking at. Let's see how this toolpath was developed. All right, to start off with, I'm going to take a look at what we have to deal with. So what I'm concerned with right now is machining this radius here. And I'm going to turn on the profiler for a second and go to a end view here. And right here you see that this radius is actually undercut slightly, which would make it really impossible to machine with a ball end mill in a 3-axis machine. So we're going to machine this in 5-axis mode. Additionally, if I take a look at that radius, it's just under a 3/8 radius, so we'll machine that with a 1/2-inch ball mill. So let's get started putting some toolpaths together. So I'm going to open up my CAM and create a 5-axis process. And I'll select this 1/2-inch end mill, 1/2-inch ball mill. And when I build a 5-axis process, I'm presented with a dialog specific to 5-axis processes. And just like any other GibbsCAM process dialog, it separates the task or the groups of parameters and controls into individual tabs. And within those tabs, particular types of parameters and controls are separated into different areas. This makes it a lot easier to focus on individual toolpath control challenges and really helps you focus on the trees rather than getting bogged down in the forest. When you're programming complex parts, the job often becomes a lot simpler and certainly less intimidating when you break it down into individual toolpaths rather than becoming overwhelmed by the overall complexity of the job. So taking a look at this, so looking at the tabs that we have a number of tabs. There's 7 in this particular environment. We're looking at options right now, and this allows us to set our speeds and feeds for the toolpath, how we want the retract to behave, a rapid or a feed retract, our coolant options, rotary duplicates if we want them. We can duplicate our toolpath around the platter, if you will, and the machining coordinate system, the coordinate system that we want the toolpath to occur in. Additionally, we have this drop-down dialog. It's currently set to general, which basically means that we have access to all 7 of these tabs, and we have control over virtually every aspect of the toolpath. And additionally, we can select particular types of 5-axis machining, projections, swarf machining, different types of 5-axis specific machining. And what happens when we select one of these is that the software in the background sets a lot of the parameters for us, parameters that are generally specific to that type of machining, and reduces the amount of data that we have to enter. So you can see for projection machining, a pretty simple page to fill out to get projection machining, and then a linking page, which we'll go over the linking page later. Another thing to keep in mind is that if you're creating a specific toolpath type, and maybe there's some aspect of that toolpath you're not entirely happy with, you can go back to the general setting, and those preset parameters are still valid in these other tabs, which means that you could go back in, if we recreated the toolpath, now it would be exactly the same as it was when we were in the projection tab, but we can go in and access control over any aspect of the toolpath and tweak it. A byproduct of that is it's a really good idea anytime you're starting a 5-axis process to hit restore defaults, just to make sure all the settings are what you expect them to be. So let's move on to the Surface Paths tab. Now, the Surface Paths is where we define the toolpath as far as the intersection or the contact point between the cutting tool and the surfaces being cut. And we can calculate that based on a number of things, including surfaces, triangle mesh, the underlying triangle mesh, or wireframe, swarf machining, multi-axis machining, which has some really nice roughing patterns in it, including adaptive roughing and 5-axis. And we also have geodesic machining, which is a different algorithm for calculating the transition between toolpath nodes. It gives you a very smooth, very consistent toolpath, and some really nice deburring strategies. For the time being, we're going to focus, though, on surfaces, toolpath based on surfaces. Moving down, we have the toolpath pattern. We have a choice of parallel cuts, and I would encourage you to kind of watch this diagram over here, this picture, which will change as we select different things. So we can see that a parallel cut is essentially straight line parallel cuts. It's very similar to a lace cut in 3-axis surfacing, except it's in the 5-axis world. We can create toolpath perpendicular to a curve, or we create some sort of curve, and the toolpath will always run perpendicular at the point at which it crosses the curve. The curve does not have to be a straight line like this shows. It can be a complex curve. One of my favorites is morph between two curves, which starts with one shape, the toolpath following that shape, and as it works its way across the drive surfaces, the surfaces that we're cutting, it transitions to a different shape at the other side. We can also run parallel to a curve. We can project curves. We can morph between two surfaces, which is very similar to morph between two curves. We can run parallel to a surface or create flow line machining. For this part, I'm just going to select morph between two surfaces. So to get started with my toolpath, I need to start making some definitions of what I want to cut. I'm going to define my drive surfaces first. So I'm just going to right-click down here and select all of those spaces, deselect that, and that leaves me with my undercut radius as the surfaces that I want to machine. Now, I've got edit surfaces that I need to define. The first edit surface is going to be this surface up here. And I'm going to click OK. And by the way, I forgot to mention, if you're in a dialog and you have an OK button in 5-axis especially, click OK to get out of that dialog. Because if you don't click OK, you lose the settings that you have set in that dialog. You need to click OK to accept those settings. So what I just did by defining this blue surface as my first edit surface, my toolpath is going to begin where the drive surface, the yellow surfaces, intersect the blue surface. I'm going to define my second edit surface as this one. All right, so we're going to start cutting at this intersection. We're going to finish cutting at this intersection. In addition, we could define a drive surface clearance, and again, the picture changes to show us what they're talking about. So this tells me that a positive number in there will actually stop short of the tool reaching the actual surface by whatever amount you enter in that field. 0 will put the tool exactly on the surface, and a negative value will impinge the surface, or it'll cut into the surface by the amount specified. This part's already been roughed, so I'm going to cut right to the finished surface. Then we can move down to the area. These are essentially modifying the area being cut. It may seem redundant since we've said we want to cut this yellow area, but we can tweak that somewhat. We can do a full cut but avoid cuts at the exact surface edges. This is going to step over the amount that we specified, but it's going to avoid making a pass at the exact edge of the surface. Or we can cut the full shape and force a start and end at the exact surface edges. This will modify the step over and force a pass at the exact surface edges, which is what we're going to do here. Alternately, we can control the area cut by the number of cuts or limit it by 1 or 2 points. So we're going to do a full cut starting and ending at the exact surface edges. Additionally, we have some further modifiers here. If there were sharp inside corners, we could control how the software handles those. We can do a bow tie, or we can have the software simulate or internally create a radius in there so that a tool larger than the radius is not gouged without having to do gouge checking on it. We can also extend or trim the tool path. We can extend it along the strokes or trim it along the strokes, and we can also extend it along or trim it along the width. We can specify the angle range that we want the tool path to occur in, or we can create 2D containment boundaries for the tool path. As far as sorting, just briefly, we can flip the step over, which just reverses rather than going from here to here. If I did a flip step over, it would start down here and go up. It just reverses the order of the strokes. We can also control the pattern, if you will, or the directionality. We can zigzag, go one direction, or spiral. Since this is a closed loop, I definitely either want to go one way or spiral, and I typically will choose spiral most of the time. So we're going to spiral, and then the direction for one-way machining, we have climb, conventional, or we can specify clockwise and counterclockwise. I'm going to specify counterclockwise. Sometimes the difference between climb and conventional is not so obvious in the 5-axis world as it is in the 3-axis world. So I'm just going to specify that I want the tool to go counterclockwise. And then we have our maximum step over. It defaults to 50. I'm going to bump that up just a little bit for our for toolpath calculation speed here at the beginning while we're still tweaking toolpath. And I'm going to go ahead and click Do It and see what the results are. I'm going to also come down here and open up my progress bar and lock it in place so that I can kind of keep track of what's going on. And what we end up with here is what looks, at least at first glance, to be beautiful toolpath. It's a very nice spiral. There's no, no abrupt step downs. It's just a smooth spiral toolpath. Cuts beautifully from the beginning of that surface to the ending of the surface. And if you don't look too closely, you might be initially pleased with this right up until the point where you simulate it. So I'm going to go to my Operation Sim, and sorry, one thing that I need to fix here. I'm going to go to my Operation Sim and watch this run, and it's not really going to be as pretty as we had thought it would be. I'm going to move this, it's a little more convenient, and hit play. And so that's probably not the best strategy for getting into the part and not the best way to tilt that tool while cutting this part. But if you look at the toolpath, the point of contact between the tool and the part is good. What we fail to do is to adequately control the axis of the tool or the center line of the tool. Some people think of it as controlling the back end of the tool. And we kind of, once you have some time in this environment, you would have realized right away just by looking at this entry move and this exit move that the tilt of that tool was not quite what we had in mind. All right, so how can we control that? Let's take a brief look at our process. And we can see that we looked at options, we looked at surface paths, and then the next tab is tool axis control. And that's what we need to do, is we need to control our tool axis. So again, we're breaking this down into pages that deal with the same set of tasks, if you will. So one thing we have here is the ability to limit our toolpath to 3-axis or 4-axis, or we can produce full 5-axis output. Of course, we're going to produce full 5-axis output here. We have a maximum angle step, and this is the maximum angle that your platter can rotate in a single toolpath node. And then here's really what we're concerned with, how the tool axis is controlled. The tool axis will be tilted relative to the cutting direction. Well, tilted relative to the cutting direction with zeros in both of these fields, 0 leader lag angle and 0 side tilt, effectively keeps that tool perpendicular to the surface being cut, which is exactly what we saw here. Other choices here are to not be tilted but stay normal to the surface, tilted with a specific angle, tilted with a specific angle relative to an axis, or rotated around an axis, or tilted through a point or tilted through a curve. Now these are very, very useful. Tilted through a point or tilted through a curve requires a point or a curve that is behind or above the cutting tool when it's cutting, and the center line of that tool projected back through the holder, if you will always be pointed or oriented to that point or that curve. Conversely, we also have tilted from point away and tilted from curve away, which is kind of the opposite. You have a point or a curve that's below or projected along the axis of the tool through the point of the tool, and the tool will always stay pointed toward that point or that curve. So I think the strategy that I want to use here is going to be tilted through a curve, and really before I can do that, I need to have a curve to tilt it through. So I'm going to select the surface and just extract the edges of it. And then I'm going to take that curve, and in my geometry palette, I'm going to offset it. And I'll offset it an inch. I'm going to get rid of the geometry that I don't need, and I'm left with this. All right, so this is a curve that's kind of parallel to, but inside the shape that I'm cutting, smaller than the shape that I'm cutting. However, with it being down on the floor of this pocket, it really doesn't do me any good, because if I project the center line of my tool through this, I'm still gouging, so I need to modify this somewhat. So I'm going to translate this up, and I'm going to go, say, a 1/2 inch a couple of times, and maybe one more time. So that's 1.5 inches above the floor of that pocket. And then I can kind of test that briefly or quickly just by rolling this thing around and kind of lining this up with the matching portion of the surface behind it, and get an idea of how much tilt is going to be required to get the tool there. And that's a good amount of tilt. I'm pleased with that. I'm not risking hitting the back edge of the part with my tool or my holder, and I can easily get to that undercut there. So with that built, I'm going to load my process back in, which reselects everything, by the way, rebuilds my toolpath and reloads my process with all the parameters set the way that they were when that process was built. So all I need to do to tweak this toolpath is come over to my tool axis control and come down and say, I want my tool to be tilted through the curve. And my tilt curve is going to be that. And hit OK. We'll recalculate the toolpath, and if you watch our entry and exit move here, you should see them realign with our tilt curve. And you see now they're projected toward that tilt curve. So let's go back and watch the simulation again. And this time I'm going to lock the simulation to the machine. I'm going to start it simulating, and we see the tool comes down without crashing through the part. If I go to home view, I'm going to be looking straight down the tool, right down the center line of the tool. And you can see that our tilt curve stays right in line with the center line of the tool right there. So controlling the tilt while it's doing this cut is very, very simple. Let's take this a step further. a lot of parts aren't really this simple. They're simple, or they may be very, very complex. But perhaps this part has more features to it than just what we see here. Maybe there's features back over in here, and some of those maybe overshadow or overhang this pocket slightly, and that can be simulated like this. So we have this piece, which we highlight that and go to a top view. We can see it overhangs our pocket a little bit. And I believe that's going to be enough that we get a gouge. We need the tool to stay away from this, but we still need it to tilt and get the undercut here without gouging. Now there would be a tendency here to tweak or to change this geometry that we're using for our tilt curve to pull this side of it back a little bit to force more tilt so the tool can get up underneath this. But that's really not necessary. What I'm going to do is I'm going to turn this into stock so that we can see it in our rendering. Let's just watch that run briefly. I'm going to lock that to part this time. I just want to see it come around here, and we should see that we're gouging. We're scalloping this feature here just slightly. And again, just imagine that this is some feature of the part that just kind of gets in the way. So rather than really changing our geometry here, what I want to do is go into my process and do gouge checking. So I'm going to go into the gouge check page, and GibbsCAM allows you 4 gouge check strategies that can be run together, and they'll actually run sequentially, or they cascade. I only need 1 gouge check strategy, so I'm going to turn 1 on, and I can check the flute and or the shank and or the front of the holder and or the back of the holder. In this case, I probably just need to check the tool. I'm not too concerned about the holder, so we'll do the flute and the shaft. Now, this column allows me to say what I want to happen if it detects an approaching gouge. Retracting the tool is very good in some situations, but in this case it doesn't help us. What I need it to do is to tilt the tool. All right, I want it to tilt the tool, and very, very often automatic works great for this. I'm just going to leave this on automatic. And then what do I want to gouge check against? I don't need to gouge check against my drive surfaces, the yellow surfaces, they're fine. But I do want to define some check surfaces. So, you know, 1/2 thousandths tolerance is fine, maybe a bit tight, but it's fine. And how much stock do I want to leave? How much distance do I want to have between the edge of my tool and the surface that it's checking against? I'm just going to give it a 1/16 of an inch. And then what are my check surfaces? I'm going to define those as being that entire body right there. And with that done, I'm going to hit redo. Let the toolpath recalculate. And I'm going to go down to an end view here and go back to my simulation. And I'm going to put my point of view lock on fixed part and run this. And what I want to see is if that tool is tilting. I'm going to slow it down a little bit. And you can already see that it's tilting below the curve as it comes around here. It's tilting more than it was on the other side to keep the tool away from the surfaces that we're checking against. I'm going to rewind that and change my point of view to the machine. And again, go to a home view, so we'll be looking straight down on the tool. And here you see our tool is centered up just the way we told it to on our tilt curve. And somewhere along in here, it should be detecting an approaching gouge, and we see that tool start moving off of the tilt curve. until it's completely off the tilt curve, and then it comes back on, but it never quite makes it centered up on it, and it tilts back off over on this side. And then as we come on around, away from the interference, the tool lines back up with the tilt curve. So I showed you that just to kind of emphasize that it's not an abrupt change. It's a very smooth transition. It detects the approaching gouge. It starts making adjustments for that ahead of time. I'm going to deselect everything, and let's go ahead and finish this part. I'm going to open up my CAM again. Let's do a little more machining. I'm going to clear that process out. I'm going to create another 5-axis process. And for this one, I need a finishing end mill. It's going to be a square end mill. A little bit of corner radius won't hurt. Those settings are fine. And I'll open that up. And since I'm going to change the style of machining pretty significantly, I definitely want to hit Restore Defaults on this. I'm going to go to my Surface Paths page. And for this one, instead of my calculations being based on surfaces, I want to base my calculations on swarf machining. And swarf machining is where you cut with the edge of the, or the side of the tool, and it's a great way for finishing ruled surfaces, surfaces where you can create a flat line, a direct line from one edge to the other at some angle. So we're going to do swarf machining. And this is going to be a roughing pass, so I'm going to keep the tool 20 thousandths away from the finished surface. And I'm going to define my swarf surfaces as being these. So that's what we're machining. And then instead of using tilt lines, I'm going to use guide curves. So I'll turn my edges on and select my upper guide curve as this. And I'm going to select my lower guide curve as that. All right, so we're saying 20 thousandths away. I've defined my upper and lower guide curves and my swarf surfaces. Now, this is a roughing pass, so I'm going to go ahead and go to multi-cuts. I'm going to tell it to do this in 2 slices. So it's going to cut halfway down and then the other half. And then in addition to that, since the bottom edge of the tool is going to be controlled by this geometry here, I want the tool to go a little bit past that. I want to ensure that I don't end up with a wire edge down here. So I can do a tool shift along the axis right here. I'm going to give it a negative 30 thousandths. And I'll close that. Let's go ahead and build in our finishing pass. I'm just going to use the same tool for it. And everything really can stay the same, except that I don't need to leave 20 thousandths stock. And I don't need to take 2 passes. I still want to overshoot the bottom by 30 thousandths though. All right, so with those set, I'm going to create that tool path, and we should see a short, a halfway down roughing, all the way down roughing, and then a finishing pass here. And that's exactly what we have. This is our cut halfway down, leaving 20 thousandths stock. Our cut 30 thousandths past the bottom, leaving 20 thousandths stock, and our finishing pass. So let's see that simulate. Let's see just that simulate. All right, so here's our swarf halfway down, and we see that red right there is kind of warning me that the tool is rapiding in contact with the part, and I expected that because we haven't controlled that yet. I will go ahead and verify that the rest of the tool path is what I wanted. So that finishes up our roughing. And there's our finishing. And again, it's rapiding in contact with the part. So how are lead in and lead outs handled in 5-axis? Let me just make sure this process is loaded. Let's go back into our roughing first. And lead in, lead outs, and really anything that has to do with how the tool gets from one place to another is handled on the link page. And we have several areas of control. Our first entry and last exit, everything about that is controlled here. Gaps along the cut, this would be if there were a small void along the stroke, or any void along the stroke, or a mathematical void, something that you can't see, but just because of tilting, that happens very occasionally, how that is handled. You also have links between slices, which is a link between two different strokes or two different slices, and links between layers. If you're doing roughing, you have multiple layers and you can control how those are handled. So on the first entry, when the tool is first getting started, I want it to use a lead in. And when it gets finished, I want it to use a lead out. Okay, that's simple enough. And then the links between slices, I'm going to have it use a lead in. Actually, let's do a lead in and a lead out. All right, so between slices, between layers, and on first entry, last exit, we're using lead in and or lead out. Now, the lead in, lead out is controlled by the default lead in, lead out, or you can specify something specific for each one of these with these little buttons off to the side. But I'm going to use the same strategy for everything. And one that works real well for, well, they all work real well for me, but one that works real well for me and it's really easy is just automatic arc. It does a great job of figuring entry exit. So I've set my lead in style over here, and then to transfer this data over to my lead out rather than having to enter anything again, I can just copy it over. Hit OK, and recalculate my toolpath. Well, actually, before I do that, let me do the same thing to my finishing pass. Come down to link, and here all I'm concerned with is my first entry and last exit. And now we'll recalculate our toolpath. All right, and there we have it. And you can see the entry exit moves over here, and we can run our operation simulation, again, just on the selected operations. And you can see the rapid in contact with the part is fixed. All right, in the, I don't know, the last half hour, 35 minutes or so, we haven't gotten in a rush. We've taken our time, and yet we programmed a 5-axis finishing pass on the undercut radius. We tweaked that toolpath. We tweaked it again to provide gouge avoidance and developed roughing and finishing toolpath for a score profile. The task associated with developing these toolpaths is laid out in a simple, easily understood manner. It makes it easier to learn, it reduces the programming time, and lessens the risk of mistakes. The speed at which you can make these changes really lets you try multiple toolpath strategies to see what you like best. I used to call it playing what-if games. What if I change this? What if I change that? The changes are so quick to make, and the toolpath calculates so quickly most of the time that it's very easy to try a couple of different strategies and see what you like, what you think is going to fit your needs the best. That concludes the presentation portion of the webinar. I think we have some time to address a few questions. During the presentation, Bart Ellers, another GibbsCAM reseller, has been collecting and collating the questions for us, and he'll join us now. Bart?
Hey, David. Thanks for the handoff. First of all, great job on the presentation. You certainly made 5-axis not look as intimidating as many people think it is. It's actually much easier than people think it is, so great job. Hey, we do have several questions, so I'll start with the first one, and this is a question for you. It said, you mentioned limiting the toolpath to 3 or 4 axes. Is there a benefit in buying the 5-axis module for shops that don't have a 5-axis machine?
I would have to say yes, definitely. If a shop does a lot of 3-axis work, a lot of 3D work, especially molds and dies, or really, any complex 3D work on a fairly regular basis, the 5-axis module provides a lot of advantages. You have additional very powerful tool paths beyond those that are offered in the surfacing and the advanced 3D, which are also really good. But it provides you additional tool paths to those. As you can see, it provides a lot of controls to those. Excuse me, a lot of controls to those tool paths. Very often, providing faster tool path. The adaptive roughing in the 5-axis is phenomenal. There are just a lot of very fast, very high-quality tool paths that will greatly benefit somebody who only has a 3-axis machine or maybe a 4-axis machine.
I would completely agree with you, and I'd expand on your answer to say there's a lot of advantages to applying 5-axis strategies to a non-5-axis part. This increases tool life, allows you to cut faster because now you can use the whole side of the tool maybe to cut a surface versus just the tip of the tool. It's better for machine wear, better for tool life. There's many advantages to using 5-axis strategies on a non-5-axis part or machine. So, and also I would add that I think that's becoming more and more commonplace in a lot of shops that they're starting to see this and they're starting to use these strategies on the 3 and 4-axis parts. All right, next question. Yeah, sorry about that. Next question, also one for you. It says, in the software I'm familiar with, I usually get a ton of retracts during 5-axis toolpath. Can you control that better in GibbsCAM?
Well, not knowing what you're coming from, I don't know better or worse, but you can certainly control it very, very well in GibbsCAM. The linking page, as I said, really kind of gives you control over how the tool gets from one place to another. Matter of fact, if y'all will bear with me for just a few seconds, let me pull up a part that I use in my training, and I use it for a little bit of a different purpose. But I think it will help explain this if y'all don't mind looking at just a slight little bit more toolpath. Bring that down. And this is just a real simple part. But let me go ahead and create some toolpath on here. And I'll do a 5-axis toolpath, and we'll just stick with that 1/2-inch end mill, 1/2-inch ball mill. I'm not going to worry too much about the details here. And I'll just do a morph between 2 curves. For morph between 2 curves, my drive surface is going to be this. And turn my edges on. And my first edit curve is going to be this one. Sorry, my first edit curve is going to be this one. And my second edit curve is going to be this one. And again, we can control this toolpath as 3-axis, 4-axis, or 5-axis toolpath very, very simply right here. I'll just leave it as it is, and I'm going to have the toolpath just stay normal to the surface. There's not a whole lot of 3D shape here. This is 3D shape, it's not flat. But let me create that toolpath. And of course, you know what I forgot to do? I broke my own rule. I didn't hit restore defaults. So it had retained some of that information. So let me just do it the right way. So we're going to do a morph between 2 curves. We have the drive surfaces set. Our first curve is going to be there. Second curve is going to be there. And now we'll create the toolpath. All right, so a couple of things that I want to show you here. First off, we have a lot of retracts. The second thing is that this line, this edge is straight, but these strokes are curving around that. As they exceed it, as they go past it, they start wrapping around it because of the way offset toolpath is handled. Now, that can be handled with this surface edge handling choice. I just say extend the edge curve and recalculate it, and those strokes will just extend on straight without curving around the ends. And that's kind of the function of this part in my training class. But also notice that we've got a whole boatload of retracts now. And again, that's handled in the link page. Very, very easy. Each of these strokes is a slice. So from here to here is a slice, here to here is a slice. And right now it's told to move directly from one slice to the next if it's a small gap. But a small gap is just 20% of my tool diameter. And then, the link between slice, it moved direct between slices, and it's 110% of my step over. My step over, I believe, is 50 thousandths. So 110% of 50 thousandths is 55 thousandths. So if this distance from here to here at that angle is greater than 55 thousandths, then it considers that a large move between slices. So a couple of things I would change here typically would be I would have it follow surfaces rather than a direct move. But also I would just change this definition from 110%, let's make it 500% of my step over. That's a 1/4 inch. So let's recalculate. And we have 1 entry move, 1 exit move, and no intermediate retracts.
No.
So the answer to the question is yes, we have very good control over retracts.
Oh, fantastic. Looks like you've got a lot of control in the toolpath. The next question is one that I'll take. It's a two-part question. And it says, if I already have a post for my machine, will it require an upgrade to support 5-axis? And the answer to that is yes. If it doesn't already support 5-axis, then you'll need to get an upgrade to do that. You can just work with your local reseller to determine what it'll take to get your post upgraded. The second part is, how about if I don't have a 5-axis machine? Then the answer to that is no. As long as you have a post that supports the machine, let's say it's a 3-axis machine, as long as you have a post that supports the 3-axis, then you don't need to upgrade it, because when you select just the 3-axis output, that's all you get is 3-axis moves. So depending on your situation, you may or may not need a post upgrade. All right. Next question. It says, does GibbsCAM 5-axis support TCPC dynamic work fixture offsets? That's for you, David.
Okay. Yes. The simple answer is yes, a resounding yes. GibbsCAM fully supports tool center point control and dynamic work fixture offsets. No issues there. Full support.
Okay. Next question also for you. You showed finishing toolpath throughout your demonstration. Can the 5-axis module also do 5-axis roughing?
Again, the answer is yes. Just real briefly, again, with almost any of the tool paths that we select on the surface paths page, we have a roughing tab where you can define roughing routines based on your stock definition, taking multiple passes, plunge roughing, morphing a pocket, depth cuts, area roughing, and so on. So there are a lot of options there for converting or for adapting a lot of the 5-axis tool paths to roughing. But in addition to that, and to me more importantly, is we have this multi-axis machining, which has great, and I mean great, roughing routines. And you can do offset roughing or adaptive roughing. Is very powerful, very flexible, very easy to use, frankly, and gives you some really powerful, very effective roughing routines. So the answer is yes.
Okay. Well, we got a couple of more questions, and then we'll end the webinar after that. The next one is, and it touches a little bit on what you were just talking about, and again, one for you is, do I have to buy the multi-blade option to program a single impeller?
No. While the multi-blade option makes programming an impeller a lot quicker and a lot simpler, as I mentioned at the beginning when we were looking at the options tab, really all those specialty cut styles do is selecting those. All that does is preset values and parameters that are available to you anyway in the 7 tabs. Now, it can be very confusing on some of these really complex parts. And the first couple of times you go through it, figuring out exactly what the combination is, and that's why there are for these really complex parts there are packages or add-ons that will handle that for you. But I've got a customer that I believe is actually attending this webinar who just recently bought the 5-axis module, and I believe the very first part that he did with it was a 5-axis impeller. He does not have the multi-blade option, made a beautiful impeller, and that was his first, I believe, either his first or second part with GibbsCAM 5-axis. Very successful. We worked through and actually used the multi-axis toolpath option roughing for roughing the impeller. Did a gorgeous job of it, very, very simply. And then the blades were mainly just a swarf cut. So it was fairly simple. Now, it wasn't the most complex impeller I've seen. We didn't, it wasn't ultra complex, but it was machined very simply by a relative novice with GibbsCAM 5-axis software, and probably took a couple of days to work through the toolpath and then machined it over this past weekend.
Okay. Well, then, would it be fair to say that if you just do the occasional turbo component, such as an impeller, you don't need the multi-blade option, which is an application-specific piece of software for doing turbo components? If you're just doing it occasionally, the 5-axis should work fine for you. It'll take a little more work, but you can do it. But if you're going to be doing a lot of turbo components, a lot of impellers, then you're probably much better off getting the multi-blade option. Is that a fair statement?
Yeah, and that's actually where I was headed with that. I just forgot to wrap it up. If I were in a job shop that maybe once in a blue moon I have an impeller to do, I don't think it would be. I don't think I would have a cost justification for buying the multi-blade option unless those impellers were really complex. For just normal impellers, if I just get them on occasion, I don't think the multi-blade option is necessary. But if your bread and butter is multi-blade, you're doing impellers, on a regular basis. I won't even say day in, day out. If you see them on a regular basis, I think the time savings in having the multi-blade option would pay for itself very, very quickly.
I agree, and I would also say the same for porting. There's a special module just for porting. Again, if you're only doing the occasional porting, you may not need the 5-axis porting module, but if it's your bread and butter, then you may want to look at it. So for those options, you can obviously just contact your local reseller, and they can explain more, demo it for you, and discuss what it takes to get those options. All right, well, one more question, and then we'll wrap up. And this one, David, we'll both kind of take turns answering, but I'll start it. What training is available for 5-axis? So in almost every module of GibbsCAM, there are many training options available that range from in-person, whether somebody comes to your site and does training, or you go to the local reseller's training center. Or it could be done online, or even Moore-Park corporate office out in California offers occasional training classes. And that's true for almost every module. It's less true when you get to more advanced applications like MTM Swiss machining or 5-axis. In that case, you're really going to be limited to, there are no online training videos available. You're going to be really reduced to working with your local reseller, and you're going to want to do that in person. Now, with that said, you could also do it online, but online live in person, not online training videos. So there's a few training options available that work very well, and again, we would just encourage you to work with your local reseller to see what training options they can offer. Any expansion on that, Dave?
Yeah, I would just say that those options are available for the wide variety of GibbsCAM options. When you get into 5-axis, learning the fundamentals from what I would call a canned course is good, but when you get to the advanced training on the 5-axis, it really needs to be based around your world. Training that I would provide for somebody who's making impellers would be vastly different from the training I'd provide for somebody that's making automotive body dies or something like that. Just different worlds. They're both 5-axis machines. They're all doing 5-axis programming, but they're doing very, very different 5-axis programming, and their training needs to come. And once you get past the fundamentals of 5-axis, the specifics need to be on the customer's parts, if at all possible. So yeah, I would agree with that.
Yeah, that's a good point. 5-axis, more than a lot of applications, you want to be doing the training on the customer's parts, because again, a wide range of different 5-axis machining. So with that, we'll wrap up. For any questions that we didn't get to, we will pass along to the local reseller so that they can follow up with you directly. But here we'll go ahead and wrap this up. And thanks for attending the webinar. And David, thanks for doing a great job.
My pleasure. Have a great day. Contact your reseller for more information or if you have any unanswered questions.